So in part 2 of this particular lesson, we're going to take a look at how to extend the Java CompletableFuture framework, which we looked at in part 1. And then we're going to show how to apply our extended CompletableFuture framework, CompletableFutureEx class or subclass, to reduce and multiply big fractions using Java virtual threads for everything, including for these more advanced completion stage operations, which heretofore would have been hard to do without these features that were added in Java 9. So we're going to take a look at the EX6 project in the Loom folder in my live lessons GitHub repository. Here we go. This is the EX6 folder. Let's start by just taking a quick look at CompletableFutureEx. This is the class I showed you briefly earlier, and I've kind of gussied it up a bit. So in this case, once again, we extend from CompletableFuture to make our own subclass. And here, we're going to do some cool things. So we're going to give names to each virtual thread so we can see what's happening when we run our program. So to do this, we're going to make ourselves a static final atomic integer called sVirtualThreadCount, which starts with 0. And you'll see what that gets used for in a second. And then down here, we're going to make ourselves a thread factory. And this thread factory will be connected to this new thread per task executor down here. And what happens is every time we need to make a new task, the thread factory is going to be called. And what the thread factory is going to do is it's going to take the runnable, which is the task. It's going to make a new virtual thread with this name. So the name is going to be virtual thread. And then we take the get and increment call here, which increments this atomically by 1 each time. So we're going to encode that. So it'll be virtual thread 0 or virtual thread 0, virtual thread 1, virtual thread 2, and so on. And then we're going to create a new virtual thread that is not running yet, and we're going to give it the runnable. And then the framework will start the thread when it needs it. So that's the thread factor that we use, just to make it a little bit more clear what's going on when we run the example. We connect that thread factory to our new thread per task executor. We make our set executor set the executor. We're going to show you why we do that later, because we want to override it to switch back and forth between this virtual thread executor and the common ForkJoinPool executor, just to demonstrate the differences. Default executor returns whatever set into that static field, which is defined right here. New incomplete future makes a new incomplete future, CompletableFutureEx. And then finally down here, supply a sync, which is really the entry point into this virtual thread spawning CompletableFuture framework thing, is going to take a supplier, make a new CompletableFutureEx, and tell it to complete this supplier asynchronously using whatever executor is configured based on how we ran how we used the set method up here to set the executor. All right, now let's go look at the main program. So here's the main program. It's going to show how to reduce and multiply big fractions using CompletableFutureEx, which is a subclass of the CompletableFuture superclass. And this needs to work with Java 21. This should say 21. You could probably get this to work with earlier versions of Java, but I just updated it to use 21. So here's what the program does. We parse the command line arguments, and this will do stuff to set, for example, the number of items we want to create and whether we want to turn debugging on or not. So we're going to create 50 random big fractions. We're then going to run the tests, and then we're going to print the results. And you'll see that when we run the tests, we start out by generating count number of big fractions that are unreduced. This is what generate random big fractions looks like. It's going to make a bunch of very, very, very big fractions, absolutely enormous big fractions. And we're going to make a gigantic numerator, a much smaller denominator. We're going to make a big fraction with the numerator and denominator. And that will be unreduced. So we're going to reduce it. Concurrently reducing takes a while. And we're going to limit it to this many. And we make a list. So that's just some good Java streams programming. And then we're going to call test fraction multiplications twice. The first time we're going to do it, we're going to pass in that list of random big fractions. And we're going to use the CompletableFutureEx with virtual threads. And then the second time, we're going to run it, and we're going to have CompletableFutures running with the common ForkJoinPool. So we set the common ForkJoinPool. And you'll see the difference in how they run. And then we'll also be able to measure the performance implications, if any, of switching between these two different versions. Keep in mind this is a compute-bound operation, multiplying, reducing and multiplying big fractions. So those are the things we're going to do, and we're going to time how long each one takes to run using our little time run method in the runtimer helper class. So here is test fraction multiplication. So we're going to basically say that we're starting up our program, and then we're going to go ahead and define a function called reduce and multiply fraction, which is going to take a big fraction and it's going to return a completable future to that big fraction. And we're going to pass that function into the map operation in the stream, as you'll see in a second. So what do? We use our CompletableFutureEx supply async method, which we wrote, to take the big fraction and reduce it. So we take the unreduced fraction and we reduce it, and that will take some time, but it'll end up with a reduced fraction. We then, after that's done, running in its own virtual thread, we're then going to start a new virtual thread in the context of this other completion stage method called then apply async. And this will create a new virtual thread in the background that will reduce, it'll take the reduced fraction and multiply it by a big constant. By the way, I should say that if we're configured to use virtual threads, this will create virtual threads. If we're not configured to use virtual threads, this will use the common ForkJoinPool, and there'll be a relatively small set of pool threads, worker threads, that will do these operations asynchronous. And then when we're complete here, we're going to display the results of reducing and multiplying the big fraction, and it's going to tell you what thread this is running in. And that will be quite interesting because it'll show you how virtual threads actually get created and used for all the pieces. After we do all that, or after we define that function, we take the big fraction list, turn it into a stream, call reduce and multiply fraction on each of those elements in the stream, and that will return a stream of completable futures to big fractions. So we get a stream of that, and then we use our futures collector, which we talked about last time. I'll just quickly go through it. We'll collect that into a single completable future. Here's future collector. Future collector is a collector that takes a stream of completable futures to type T, stores them in a list of completable futures to type T, and then returns a completable future to a list of items of type T after everything's done running. And we use an array list internally as the mutable result container. We use the list add method to accumulate things into our list of completable futures. We don't use the combiner because this is a sequential stream. And then finisher, this is the one that does all the interesting stuff. It takes the list of completable futures, converts it to an array, calls the arbitrary arity method all of on the completable future class. That will return a single completable future, which will complete when all the stuff running in the background is finished. And then when that happens, we go ahead and take the list of completable futures, which have now completed. We convert them into a stream of objects by using the join method, which will not block because we wouldn't have gotten here if there were any completable futures that weren't done. And then we return the results as a list. This comes back as a completable future to a list. So we have a single completable future that will trigger when all the other ones are done. And then when that's finished, when we're finished with everything, we're then going to go ahead and sort and print the list. Last piece of the puzzle here is to take a look at the sort and print list method. It takes a list of big fractions that have been reduced and multiplied, and it does something very cool. It uses the CompletableFutureEx class to quick sort the list and heap sort the list in parallel using virtual threads. So when we do supply async for this quick sort and supply async for this heap sort, new virtual threads are created. Those virtual threads will do sort with quick sort and sort with heap sort. And then we use the magic of the except either completion stage method, which will take whichever result comes back first, heap sort or quick sort, and then we're going to go ahead and print the results out in sorted order. So just a fun little example of how to use virtual threads in conjunction with our extended version of Completable Future in order to speed things up. So, armed with all of that, let's pop out of here. And you can see that we're done at this point. So let's run the program and you'll get a chance to see what it's doing. So I think I have debugging turned on. Yes, I have debugging turned on right now. So we'll go take a look at what it spit out here. So you can see what we do when we're debugging this is we're actually printing the thread where the computation took place, where we did the multiplication and reduction. And as you can see, these are all the different virtual threads. There's a different virtual thread for every computation. And there's a lot of them. You can see we have a lot of virtual threads. And at this point, we've got basically 100 of them. And this is the results we get, which are sorted accordingly. When we converted to use the common fork join pool, now you can see what happens. We're using a very small number of threads. You can see it basically goes from, I think, 1 to 9 or something like that. And so there's a much smaller number of threads. It's a pool of them. And as a consequence, we don't have as many threads. But the other threads were virtual threads. And let's see, if, just for kicks, I'll run this again, turning debugging off, which will give us a little bit more accurate representation of true performance. So let's turn off debugging. And let's also, just for kicks, let's have more of these guys so we can run them. Now we have 100 of these. And this should run. It'll show us the performance differences between using virtual threads versus using the pool of threads. And the results are actually kind of interesting. So here you can see that they're very similar. In this case, the common fork join pool executed ever so much faster by just a small amount. But what I've found when I run these tests repeatedly, oftentimes it'll switch back and forth. So sometimes virtual threads run faster. Sometimes the common fork join pool runs faster. Yeah, there you go. So this time we ran it. Virtual threads were a little faster. But I mean, we're talking about minuscule amounts of milliseconds faster, like 50 milliseconds faster. That's within the noise range of the precision of collecting the timing results. So bottom line, virtual threads can be used for operations like this, which are computation intensive, and they perform very well. And it's cool because we can then combine them with the programming abstractions from Completable Futures, but use the virtual thread model for the actual execution. So this is an example from Java 9 showing how using the Java 9 features with virtual threads to show that combination.